This is the third lecture of week 9, and we're going to talk about internal and external validity using the test score example. So the objective of this lecture is to assess the threats to the internal and external validity of the empirical analysis of the California test score data. So in order to test if the result is externally valid, we're going to compare the results from California to Massachusetts. And in order to test if the result is internally valid, we're going to go through the list of 5 potential threats to internal validity that we discussed in the previous lecture. So we're going to first check for external validity of the California study by looking at the Massachusetts data. So Massachusetts data set consists of 220 elementary school districts, and it includes the variables such as student to teacher ratio, test score, percentage of English learners, percentage of students who are on reduced lunch, and the district income. Here's a summary statistics of data sets from California and Massachusetts. You can see that the average test score of the student is higher in Massachusetts, and the student-teacher ratio is lower. The percentage of English learner is much lower, and the percentage of receiving school lunch subsidy is also much lower too. The school district income, on the other hand, is about $3,000 higher than California, and you can see that California, the number of observation is higher. Also, note that the data set for California comes from 1999, whereas that for Massachusetts actually comes from 1998. Here's a graph that plots the test score against district income. As you can see, for the higher district income, the linear regression doesn't fit the data points as well as the linear log regression model or the cubic regression model. So here in this table, we are showing 6 different regression models with the dependent variable that is a test score and our main coefficient of interest, which is the student to teacher ratio. Each regression model includes different independent variables or control variables, and the stars actually represent the statistical significance. So if it has 1 star, then it means that it's statistically significant at 5%. And if it has 2 stars, then it's statistically significant at 1%. So the first regression model regresses test score on just student to teacher ratio, and we get negative 1.72. The second regression model regresses a test score on student to teacher ratio, as well as the percentage English learner and the percentage of students receiving reduced lunch or free lunch and district income. So these 2 characteristics control for economic characteristics of the school district. As you can see, the coefficient that we're interested in, actually the size declines by more than half, which indicates that first model that only regresses test score on student to teacher ratio likely suffers from omitted variable bias. Now let's compare the model 3 to model 2. So in model 2, we included district income in log, and in model 3, we're including the district income in quadratic and cubic form. So both of these models are taking into account that district income is non-linearly related to test score, as we have seen in a couple slides before. But one model is accounting for that by using the log of income, whereas model 3 is using the polynomials to account for nonlinearity. As you will see in the next slide, The adjusted R-square is a little bit higher for Model 3, and the coefficient doesn't change that much from Model 2 to Model 3. So it does decline by 0.05, but it's basically the same. So we actually prefer Model 3. So as you can see here, the adjusted R-square for Model 3 is slightly higher than Model 2, and the coefficient of interest was still statistically significant for Model 3 at 5%. It seems like modeling the district income in polynomial rather than log is a better fit for the data points that we have on hand. Let's look at Model 4. So Model 4 is testing if the relationship between test score and student-to-teacher ratio is nonlinear. So we're including polynomial functions of student-to-teacher ratio in Model 4. And as you can see, both of the quadratic and cubic term of student-to-teacher ratio is not statistically significant. And you can see that because it doesn't have any stars, so it's not statistically significant at 5% or 1%. So it seems like the linear model is probably a better fit. Here you can see the F statistics and p-value for testing if student-to-teacher ratio quadratic term and the cubic term is equal to 0. And you can see that the p-value, which is 0.641 in this case, is larger than 0.05, which means that we cannot reject the null that the polynomials are actually equal to 0. So because of the F test and also the individual coefficients of quadratic and cubic terms were not statistically significant in previous slide, we can conclude that the linear model is a better fit for this data set. Next, let's look at the regression model 5. So up until now, in regression model 2 through 4, we included the continuous measure of percentage of English learners. In model 5, we're going to include a binary version of the percentage of English learner, where it equals 1 if it's greater than the median, and otherwise it equals 0. We're also going to include an interaction term between this binary version of the high percentage of English learner multiplied by the student-teacher ratio. So basically, this is testing if the effect of student-teacher ratio is different in districts with high percentage of English learner. As you can see, the coefficient is not statistically significant at 5% or 1% or even at 10%. So it seems like the effect of student-teacher ratio on test score doesn't vary depending on the percentage of English learner in the district. Regression model 6 excludes the percentage of an English learner from the regression model. So in regression model 3, the percentage of English learner coefficient was not statistically significant. So in model 6, we don't include them and see what happens to our coefficient. It looks like our main coefficient of interest actually doesn't change much from model 3 to 6. So we'll say that it really doesn't matter whether you include the percentage of English learner in the model or not, and we're going to use model 3 as our main model. So to summarize the findings from using the Massachusetts data set, first, we found that the coefficients on student-to-teacher ratio fell by more than half when we included controls for student and district characteristics, which indicated that the original model that only included the student-to-teacher ratio probably suffered from omitted variable bias. Also, the class size effect was statistically significant at 5% level, even after controlling for student and school district characteristics. There was no evidence that there is a nonlinear relationship between test score and student-teacher ratio. And lastly, there was no statistical evidence that the interaction term between student-teacher ratio and percentage of English learner was statistically significant. So to compare the results from Massachusetts to that from California, we found that the class size effect falls in both California and Massachusetts when student and district control variables are included in the model. We also found that the class size effect or student-teacher ratio coefficient were statistically significant in both of these data sets. And in fact, the estimated effect or the size of the coefficients were similar in both states. Neither of the data set actually showed any evidence that the interaction term between student-teacher ratio and percentage of English learner was statistically significant. The only minor difference between these two states was that seems like in California data, there was some evidence of nonlinear relationship between student-teacher ratio and test score, but in Massachusetts data, we didn't see that. Now let's look at the potential threats to internal validity. First is the omitted variable bias. So are there any factors that are potentially missing from the regression model? One omitted variable could be students' access to outside learning opportunities. Another one could be other district quality measures such as teacher quality. So for example, teacher quality can be correlated with our student-to-teacher ratio, which is our main variable of interest. If better teachers or teachers who are better quality are more attracted to schools with fewer student-to-teacher ratio. Of course, the teacher quality directly affects the test scores. So teacher quality could be one of the omitted factor. In order to control for these omitted factor, we have included some demographic measures as well as district characteristics such as district income and percentage of students eligible for free or reduced price lunch. And these control variables doesn't necessarily have to have a causal meaning, but they need to be correlated with the omitted factor or factors that we think are omitted from the regression model. So are these control variables actually controlling for omitted variable? The answer to this question is subjective, but there's some evidence that the control variable is actually doing its job. First of all, the student-to-teacher coefficient, which is our main coefficient of interest, doesn't change much when we include different specification of the control variables. And also, if there is an omitted variable bias, then just because the coefficient for both the California and Massachusetts were similar, the omitted variable bias for both of these data sets must be similar as well. So second threat to internal validity is the wrong functional form. So in both of these data sets, we have tried many different specifications, and we saw that there's some evidence of nonlinear relationship between test score and student-teacher ratio in California. And so since we tested many different forms, we think that the baseline model that we have is correct. The third threat to internal validity is the errors in variable bias. So in our case, both of the data sets actually come from administrative record. So it's unlikely, because it's not a survey data, it's unlikely that it suffers from major measurement error. However, because the student-teacher ratio is a district-wide measure, so it's not measuring individual student-to-teacher ratio, some of the students may actually not experience the actual district-wide student-to-teacher ratio. So for instance, if the student-to-teacher ratio in a certain district is, say, 10, there will be some students who have less than 10 students per teacher ratio in their school, and there are going to be some students who have more than 10 students to teacher ratio in their school, just because we're taking an average student to teacher ratio at a district level. So the ideal data set would be an individual data set where we see individually what the student to teacher ratio is. So fourth thread is the sample selection bias. And in this case, the sample comes from all elementary public school districts. So there's no reason to think that there is some sort of a selection bias. If, for instance, if the sample only came from school districts with high test score, then there could have been some sort of a selection bias. But in our case, since the sample is coming from all the school districts, there's no reason to believe there's a selection bias. The fifth thread is the simultaneous causality bias. And this is when your dependent variable actually affects the independent variable, as well as your independent variable affecting dependent variable. And we talked about potential policy that could exist, such that if government is giving money to hire more teachers for schools that have a low test score, this can be a problem and invalidate our result. But for the period that we're looking at and for the states that we're looking at, this type of government policy was not in place, so we don't have to worry about this threat.